Hi there, I'm Ian Dinwoodie. I'm a senior software engineer at Vector. I lead a research and development team for the unit testing tool in VectorCAST. Today I'm here to talk to you about coded tests in VectorCAST, which is a new opportunity of unit testing for the VectorCAST product line. Alrighty, so for today's presentation, we're going to first start by talking about what are coded tests. Then we're going to go over some examples of their usage, and we'll also talk about where you can get help. So coded tests were introduced into VectorCAST C++ in 2024. It introduces vUnit, which is an xUnit-style API testing framework for test cases written in C++. Being an xUnit-style framework, its interface is very similar to popular other testing frameworks such as Google Test, CPP Unit, Boost Test, and Catch2. One of the benefits about how this new testing style was integrated is it can work alongside existing VectorCAST environments and alongside existing VectorCAST test cases. So you may write new coded test cases without changing or getting rid of your existing test cases. An additional benefit is the new coded test workflow works with all the VectorCAST testing features that our customers are already very accustomed to, such as execution and reporting. You can get coverage, you can insert probe points, and many other benefits. One of the requirements of this new workflow is that your compiler must support the C++11 coding standard. All right, so let's review the use of coded tests by example so we can learn about what its capabilities are. So the coded test feature, the main purpose is it makes testing C++ easier, especially for those users who are used to writing code. So for example, if you use an API like some sort of class method or the constructor to create an object, in the coded test workflow, you will just create that object as you normally would in your code. You can just initialize an object and call any setup methods you need, or you can set it up in the code itself by assigning values to its member variables. Additionally, coded tests allows you to write any C++ code that you can normally write. That includes control flow logic such as loops and logical conditions, switch statements. This allows you to iterate through different parts of your testing, especially if you need to check different conditions in a list. You can also control when you are evaluating your logic. So in VectorCAST parameter tree-based tests, we're normally making assertions at the beginning, at the end of a test execution. With coded tests, you have control. You can put assertions anywhere you would like into your test, be at the beginning, in the middle of a calculation, at the end. A general rule of thumb is if you find yourself writing a lot of user code, then you might have an easier time implementing your tests through the coded test workflow. The coded test workflow gives you greater control to the lifetime of your objects. So some objects have global, static, local, and various scopes of lifetime. With coded tests, you are creating and you have the option to deallocate objects all when you want to. So it also gives you easy control to allocate multiple objects. You can create a list of objects, any STL structure of objects you would like. You can add and remove at will and make assertions about any point about items in that list and their state. Let's talk about test reuse. Coded tests allow you to define helper functions in your testing file, and those helper functions can be used by any of your tests. So instead of tediously setting up objects or handwriting implementations individually for every single test, if you have common actions that you need to be performed, you can just write one function and call that in any test that you need. So some examples of that, like we said, are object setup or reset function calls. So if you need to initialize an object state, like potentially you need to create and populate a database object, that could be put into one function call that all of your tests could use. Additionally, you may want to reset that database into its initial state. You can easily implement a reset call that any of your tests can call when they need the database to be emptied. Another example is a CRC function, where you can calculate a checksum from some sort of data object and verify its correctness. So you can put in a CRC helper function and pass whichever objects you would like to it without needing to rewrite that CRC code multiple times. Additionally, one of the benefits is you can write generic tests that can be applied to different parameters. So if you are trying to test how some of your code works with different types of containers, maybe it's list and vector or a set, you can write very similar code. You could even copy and paste the test below and make small edits, such as just changing the container if your testing conditions remain relatively the same. This sort of workflow allows us to proliferate tests at a very fast rate. Now let's talk about stubbing and mocks. So first, a distinction between the difference of what we would normally consider stubs and mocks. While there is not a concrete definition, the general community for testing defines stubs as an object that has controlled behavior. And a mock is a similar object, but it is also an object that allows you to make assertions about the incoming and outgoing behavior of that object. So VectorCAST has always supported stubbing, and it has always allowed you to write user code expected values inside those objects, which encapsulates mocking behavior. So we take a very similar approach here. We have the ability to do the same sort of work with the coded tests mock objects. However, the implementation is slightly different. So in coded tests, you will create a mock session object, and that will manage the lifetime of all the mocks you create for that session. The workflow for defining mocks is relatively straightforward. So you first say, I want to mock a function by requesting a mock for the function and its signature. And you assign it a function that you've created with an equal signature, saying, I want this behavior instead. And then you can enable or disable mocks in your code. So by default, they'll be enabled, but there may be cases where you would like to disable them, such as if you enter into a mock object, you may want to make some assertion about the state, such as the incoming parameter is true, and then you may want to forward that call down to the underlying function. So in that case, we would enter the mock, make our assertions, and we would disable the mock and allow it to call to fall to the real code below. So some examples of when we would use mocks. So mocks are really helpful when you need to get control of your code, and the control is not as simple as setting a variable. So you may have classes that are dependent on other classes, and there's a whole tree structure of objects falling below. But you just need control of that interface that you're working with. So in that case, you might mock the object that you're interacting with. And for example, it could be a database. In that database, you might want to say, I want the number of entries existing in the database. And by mocking the database, you can either can a response, so you could say just return the value of 2, or you could pre-populate with that mock so that you know it has 3 entries that exist in there, and you know what that value will be returned. This allows you to have control just at the boundary of your tests, so that you're not testing other dependencies. You're focusing your tests on the code that you want to test, and you know that your dependencies are controlled. All right, so let's talk about fixtures. Fixtures are a very powerful and useful part of testing. So the VUnit framework allows people to write tests with fixtures. And a fixture is simply a class. It allows you to optionally define setup and teardown routines. You can also organize your helper functions within that class so that if you have multiple tests that will use a function, you may define that helper function within that fixture so that you know which test that helper function applies to. The same goes for variables and data. So let's talk about what the purpose of the setup and teardown functions are. It's very common that you need to have your tests starting at some operational state, be it a database that has entries pre-populated. So you may use your setup routine of a fixture to create that database and populate it with some basic information. Now every test that inherits that fixture will begin at that base point. So some other examples of when you might want to use a fixture with your test. So if you have a class instance that you want to be used in every test, so if every test is verifying, my class, then you might use a fixture that creates an instance of my class so that every test can use that object equally. Additionally, if you're setting up stubs and mocks in your tests, and you know that every test might reuse those stubs and mocks, it's a great place to create them in the fixture. That way every test is starting with those functions and objects mocked out. One further example is if you write a checksumming function, you may want to reuse that for those tests, and that you know that that checksum function applies to the tests in that scope. So you might create that within the fixture so that every test has access to that. When you create an object in a fixture, it is directly accessible in the test case's scope. So if you define some object X, it will be accessible within that test case as if it was created in that test case itself. So when not to use coded tests? There are some scenarios that are conceivable where a user may flourish with the parameter tree-based testing instead. So one example is when you have a function that sets global or unaccessible state for many variables program-wide, you may find it easier to write the VectorCAST tests with that, i.e. your code is not working on a simple object-based return sort of workflow, and variables are not always accessible. Additionally, the parameter tree testing does try to account for changes in your code and make intelligent guesses about when your underlying code has changed. It tries to guess how the existing test can apply to it. But coded tests is very tightly coupled with your coding definition. So just like when you write unit tests with other frameworks, if you change an API for your code, then you're going to need to change your coded test definitions to account for those new APIs. One other common scenario where you may want to choose parameter tree-based testing is when the testers are not as familiar with the source code. We see this in environments where developers work on developing the code and they pass on a list of requirements or expected tests into a part of the QA pipeline of the software development cycle. This is usually a group of people who test full-time and take that work off of the developers. So while the developers may have intimate knowledge of the source code, the testing group might be working with a higher level of knowledge of what the code is supposed to look like. In those cases, the visual keys of the parameter tree-based models may work for them. That allows them to click through the code and see a layout of the data and the structures in front of them and make tests based on that. Another instance is for customers who do requirement-based testing. It may be a little simpler for them to look at the requirements and look at the parameter tree and see how the test in the parameter tree is mapping to the requirements. However, it is worth noting that our coded test does allow you to map requirements to the test using comments. Lastly, when you're writing your coded tests, there is the potential that you will incorrectly code your tests. Code can have bugs, and writing tests as code does not inherently eliminate that possibility. So the parameter tree-based testing may be a less error-prone way to write your tests because you're just assigning values. There's no potential to mistype or write compile errors. However, if you do go down the coded test route, you do get the help from the compiler telling you when you've mistyped something or done something wrong. A final case where you might consider the parameter tree-based workflow is when you have a lot or a very complicated stubbing workflow that you need to set up. The parameter tree lets you click and assign stubbing values, and you may find that more straightforward than working through the examples of allocating and enabling and disabling various different stub behaviors. You can get help about the coded tests by referencing VectorCAST C++ user guide. That would be in the help and user guide context menu. There's a section on using coded tests in the user guide. Additionally, in your distribution of VectorCAST, there is a vUnit subdirectory which distributes the framework, and a subdirectory of that has a docs folder. In that docs folder, there are markdown files outlining the different use cases and interfaces and examples of how and when to use coded tests. There's also an FAQ document to answer some simple questions and a reference for all the different macros that are included. Furthermore, because that folder includes a distribution, you can also look at the include and the source to get a deeper understanding of how the code works and is arranged. When we talk about coded tests integration with VectorCAST, we've also included it in the integration with VectorCAST's VS Code plugin, the VectorCAST Test Explorer. I'm just going to give you a short demo of the use of coded tests in that workflow. So I'm going to open an existing workspace of a VectorCAST Test Explorer. And so we see the Flask here appear for the VectorCAST Test Explorer, and we see that our tests are listed. So in this case, we have a normal parameter tree based test here selected, and we have a coded test. From here, we can always go and edit the coded test file. And here we see a VectorCAST test case written as code using the vUnit framework. So now we can execute these tests. And we see that the Test Explorer indicates their pass and fail value in the test tree on the left. And we can even go and view its results. So this is one example of how we've enabled the coded test feature to work with existing VectorCAST products and alongside traditional parameter tree based testing. So in summary, coded tests are a powerful addition to the VectorCAST toolkit. They provide a new and powerful way to write your unit tests for VectorCAST C++ while still being operational with the existing parameter tree workflow. They are very useful for defining tests that are involved, that may involve many objects, different function calls, complicated setup and teardown routines. One of the benefits that the coded test provides you is control on a coding level and flexibility. You really get the freedom to define tests and helper functions and object lifetime for your different objects used throughout your tests and shared between your different test cases. It allows that control to be in the user's hands. One potential difference is that it does not have the test script maintenance feature of the traditional VectorCAST parameter tree based tests, so that when you do change the interfaces of the units under test, you will need to equivalently adjust your test cases to account for those new interfaces. So that concludes this presentation. Thank you for your attention, and I will now answer any questions you have about this material.